Borates are the name for a large number of boron-containing oxyanions. The term borates may also refer to tetrahedral boron anions, or more loosely to chemical compounds which contain borate anions of either description. Larger borates are composed of trigonal planar BO3 or tetrahedral BO4 structural units, joined together via shared oxygen atoms, and may be cyclic or linear in structure. Boron most often occurs in nature as borates, such as borate minerals and borosilicates. Structures. The simplest borate anion, the orthoborate ion, BO3-3, is known in the solid state, for example in California 32. In this it adopts a near-trigonal planar structure. It is a structural analog of the carbonate anion CO2-3, with which it is isoelectronic. Simple bonding theories point to the trigonal planar structure. In terms of valence bond theory, the bonds are formed by using sp2 hybrid orbitals on boron. Some compounds termed orthoborates do not necessarily contain the trigonal planar ion. For example, gadolinium orthoborate, GdBO3, contains the polyborate B3O9-9 ion, whereas the high-temperature form contains planar BO3-3. Boric acid. All borates can be considered derivatives of boric acid, B3. Boric acid is a weak proton donor in the sense of Bronsted acid, but is a Lewis acid, i.e., it can accept an electron pair. In water, it behaves as a Lewis acid, accepting the electron pair of a hydroxyl ion produced by the water autoprotolysis. So, B3 is acidic because of its reaction with O from water, forming the tetrahydroxyborate complex, 4, and releasing the corresponding proton left by the water autoprotolysis, B3 plus 2H2OB-, 4 plus H3O plus. In the presence of CIS diols such as mannitol, glucose, sorbitol and glycerol, the pKa is lowered to about 4. Polymeric ions. Under acid conditions, boric acid undergoes condensation reactions to form polymeric oxyanions, 4B-4 plus 2H plus B, 4O, 52-4 plus 7H2O. The tetraborate anion includes 2 tetrahedral and 2 trigonal boron atoms symmetrically assembled in cyclic structure. The 2 tetrahedral boron atoms are linked together by a common oxygen atom, and each also bears a negative net charge brought by the supplementary O- groups laterally attached to them. This intricate molecular anion also exhibits 3 rings, 2 distorted hexagonal rings and 1 distorted octagonal ring. Each ring is made of a succession of alternate boron and oxygen atoms. The tetraborate anion occurs in the mineral borax as an octahydrate, sodium boride O54-8H2O. The borax chemical formula is also commonly written in a more compact but equivalent notation as sodium boride O710H2O, simply by converting stoichiometrically 4O- as 2O2- and 2H2O. Sodium borate can be obtained in high purity and so can be used to make a standard solution in tetrametric analysis. A number of metal borates are known. They arise by treating boric acid or boron oxides with metal oxides. Examples hereafter include linear chains of 2, 3 or 4 trigonal BO3 structural units, each sharing only one oxygen atom with adjacent unit. Diborate B2O4-5, found in magnesium boride O5. Triborate B3O5-7, found in CaAlB3O7. Tetraborate B4O6-9, found in lithium boride O9. Metabarates, such as LiBo2, contain chains of trigonal BO3 structural units, each sharing 2 oxygen atoms with adjacent units, whereas NaBO2 and KBO2 contain the cyclic B3O2-6 ion. Borosilicates. Borosilicate glass, also known as Pyrex, can be viewed as a silicate in which some silicon oxide -4 units are replaced by BO5-4 centers, together with a cation to compensate for the difference in valence states of C and B. Because of this, substitution leads to imperfections. The material is slow to crystallize and forms a glass with low coefficient of thermal expansion and is resistant to cracking when heated. Unlike soda glass, minerals and uses. Common borate salts include sodium metaborate NaBO2 and borax. Borax is soluble in water, so mineral deposits only occur in places with very low rainfall. Extensive deposits were found in Death Valley and transported out using the famous 20 mule teams. Later, deposits were found at Boron, California, on the edge of the Mojave Desert. The Atacama Desert in Chile also contains mineable borate concentrations. Lithium metaborate, a lithium tetraborate, or a mixture of both, can be used in borate fusion sample preparation of various samples for analysis by XRF, AAS, ICP-OES, ICP-AES and ICP-MIS. Borate fusion and energy dispersive X-ray fluorescence spectrometry with polarized excitation have been used in the analysis of contaminated soils. Disodium octaborate tetrahydrate is used as wood preservatives of fungicide. Zinc borate is used as a flame retardant. Borate esters. Borate esters are organic compounds of the type B3 where R is alkyl or aryl. They are conveniently prepared by condensation reaction of boric acid and the alcohol B3 plus 3ROH B3 plus 3H2O. A dehydrating agent, such as concentrated sulfuric acid, is typically added. Borate esters are volatile and can be purified by distillation. This procedure is used for analysis of trace amounts of borate and for analysis of boron in steel. Like all boron compounds, alkyl borates burn with a characteristic green flame. This property is used to determine the presence of boron in qualitative analysis. Borate esters form more spontaneously when treated with diols such as sugars. Trimethyl borate B3 is used as a precursor to boronic esters for Suzuki couplings. Unsymmetrical borate esters are prepared from alkylation of trimethyl borate. Argon diboride plus 2H2O, argon diboride plus 2HOCH3. These esters hydrolyze to boronic acids, which are used in Suzuki couplings.